Okay, let's resume. So I'm going to talk about routing protocols now. All right. So routing goes a long way back, and the earliest incidence of having routing goes back to what we call circuit switch networks. So the traditional circuit switch network would be your wired telephone network. The wired telephone network. Okay. And what the switch does is to connect you between A and B. All right. So in the old days, I don't know, you might have seen pictures of almost like a factory floor. You have people who are sitting in front there and they poke here, poke there, poke here, poke here to connect people, right? In the old days. That was manual switching. Manual switching. Then later we have mechanical switches. Then of course, electronic switches. So today we have electronic switches, okay? So as I said, the public telephone system is a classic example, and it's a tree structure. All right? Okay, tree structure. So for example, if I take out a wired phone line, and you know in NUS most of our numbers start with 6516, right? 6516. All right? So if I call another number that's 6516, I actually don't need to call all 6 digits, especially if it's in NUS. I just call the last 6 digits, it will reach there. Okay? So the wired telephone exchange that serves this part of Ayer Rajah Clementi, do you know where it is? You know Dover Road next to Singapore Polytechnic, the tower that looks like that one, all jutting out, is at the basement. That's where the telephone exchange is. Okay, that's the telephone exchange. So what we are more interested in is not the circuit switch network, but the packet switch network, because we're dealing with data packets. All right, and it's much more complex, obviously, compared to the circuit switch network. And these are some of the characteristics that we desire of that packet switch network. That it does the right thing, it's correct, it's simple, it's robust, it's stable. There is fairness in terms of access to the resources. It works in an optimal fashion, and it is efficient. All right. So, in general, usually for all the routing decisions that needs to be made, you need certain types of parameters to determine whether you have good performance or not. And two of the common ones that I often use is the number of hops to get to your destination and least cost. Cost not necessarily in terms of dollars, cost in terms of performance. So cost could be a combination of packet drop rate, latency, in terms of actual communications, how long you have to queue to get out, etc. So all this can add up to cost, okay? And the cost is some metric that you use. So you want to choose a route that has the lowest cost as a result. And we'll give you a couple of examples of how these costs are being calculated. So in selecting a path, there are actually two things. One is to determine the path itself. The other is to determine when to do the path. Because you cannot be always doing all the time, looking for a path. Nobody's asking for it. Okay? So there are two aspects of it. Alright? And of course, in selecting the path, the costing mechanism comes into play. Alright? Some algorithms don't use cost, some algorithms use reward. So you want maximum reward. Okay? Right? And if these are the two parameters, you want minimum cost and least cost and minimum hops. Alright? In terms of when to activate the route search, okay, there can be two options, either on demand, or you may have some pre-assessment of the whole network such that when a request is needed, you have partial information already so that you can complete the search for the route in a much quicker way. Okay, so those are the two. Okay, and we will, again, as I said, we'll see examples of that. So these are some of the routing strategies: fixed routing, alternate routing, flooding, random, and adaptive. Okay, fixed means you build a table. You build a table. All right, so in this example, with a table, we have 6 nodes that want to connect to each other, and how they get from A to B. All right, so the diagonal, of course, is blank because it's to itself. All right, so if you want to go to node 1, it's direct connected, so it's just there, 1 to 2. When you go to node 3, it goes via number 5, etc. Okay, so basically you're building a routing table here. Very simple method, but not very scalable. Not very scalable. Okay, for small networks, fine. Next is alternate routing. So this one gives you a bit of redundancy now. That means from A to B, you may have more than one path. Okay, so if one path is down, you can take another path. So that's called alternate routing. Okay, again, not very scalable. Okay, hard to maintain. So small networks, okay. Third one is flooding. Flooding means that you want to send something, you flood all over the network. Of course, it will get there. Even, the one that takes the shortest path or least number of hops will arrive earlier. But then you've got a lot of multiple copies coming along the way. So it's very inefficient, but very robust. Very robust. The message will definitely get there. Okay, that's flooding. So you get multiple copies. Although it's so simple and so inefficient, it's still a very popular method for control and signaling in a network. When you need to send control messages, flood it, flood the network. Because control messages are usually very small packets. Okay? So that is quite a common approach in many networks for control packets. So here's an illustration of that. So in this example, A will send out data, right? Then hop 2, so it sends out, it will reach B, F, and E. And these 3 guys will again flood the network, except in the direction where it comes from. Except in the direction where it comes from. So B will flood it this way, F will flood it this way, E will flood it this way, etc. Until it reaches the destination. Let's say if the destination is L. Now, an alternative to flood, the advantage of flooding is that it's very robust. You will definitely get the message and many, many more. Okay? That's the advantage. Alright? But again, it wastes a lot of bandwidth. Especially if your network does not have a lot of bandwidth. So, right? So you have to throw away a lot of duplicate packets. And because the packets follow every possible path, it's very reliable. So it's good for emergency messages, as I mentioned. Okay? And at least one packet will arrive with the minimum cost route, at least one. And then all the multiples will come later. Okay? Alright, so all nodes directly connected to the source will receive the message, obviously. Now, a variation of that would be random routing. In other words, you don't send out to all your neighbors. You send it to a limited subset of your neighbors, randomly. Okay, that's random routing. Simple and robust. Similar to route flooding, but reduces the traffic load created by flooding. So each station randomly chooses one of its neighbors to send the packet. Okay? So the probability of sending will depend on how many neighbors it has. Alright? So station is selected from the nearest, excluding the station where the packet comes from. So this is the probability. Alright? One way and not the only way. Data rate of link I divided by sum of the data rates of all the nearest neighbors. Okay, so each of them has a certain probability. Okay. Then, of course, the most powerful will be adaptive routing, and there are many variations of adaptive routing. So it's used in most of the modern day packet switch networks now. And the type of routing decisions is determined by or influenced by failure and congestion situations. The load information or cost is usually derived based on certain parameters, all right? And based on those costing, you determine what is the best path, okay? And you do that adaptively, right? So, usually for adaptive routing, you do need some local information, some information in your neighborhood, maybe one hop away, all right? So the first node in the path from the source to the final node is chosen by taking the path of the minimum number of packets queued ready for transmission. Because if the outgoing queue is very long, it will take you some time before you even get a chance to get out. Okay? So if you have multiple queues, then it becomes more complicated. So to know that, it will depend on local information, all right, that is within that vicinity. It may not be, indirect sampling means that may not be the exact parameter that you use, you're using a proxy parameter. Okay? So in this case, the queue length is really a proxy parameter, if you like, because the queue length is an indication of latency, how long you get out. Okay? Alright? On top of that, you can also add additional parameters, and one of them is called bias. Okay, we'll have an example of what bias is. And bias is used to provide some sort of a weightage of what could be better routes compared to other routes. Okay, right? So the best is to look at the example. So we have a network here. Okay, so the bias is a value that you will assign according to the cost. Okay, so in this particular example, we are saying that the path that has lowest cost we set to a bias value of 0. Next lowest cost, a bias value of 3. Next lowest cost, bias value of 6. And next lowest cost, bias value of 9. Okay, so if I want to go from 4 to 6, I want to send data from 4 to 6. I can either go 4, 5, 6, I can go 4, 3, 5, 6, 4, 3, 6, etc. And every one of these will give you, what you have on the arrows here is the cost of transmitting on that link. Okay, the cost of transmitting on the link. So you can see that if I go 4, 5, 6, the cost is 1 plus 2, which is 3. If I go 4, 3, 5, 6, 4, 3, 5, 6 is 3 plus 1 plus 2, which is 6. 4, 2, 3, 5, 6, 4, 2, 3, 5, 6 will be 2 plus 3 plus 1 plus 2, which is 8. So you can do all this and find that this is the lowest cost, therefore I set it to bias of 0. Next lowest cost, set it to bias of 3. Next lowest cost, set it to bias of 6. Next lowest cost, set a bias of 9. Okay, so now I use this together with some other performance metrics. So I'm going to combine that with the queue length. And then I get an aggregated score of whether I go in this direction or that direction. Okay, so if you look at this, to go up from node 4 to node 5, although this has low cost, it has a queue length of 5 here. There are 5 packets here. So if you are the guy behind here, you've got to wait until the other 4 gets up. Because the queue length is 5. Okay? Going out on 3, there's a queue length of 1. Going out on 2, that means from here go out to 2, queue length of 3. Going out on 1, queue length of 2. Now you have the you previously calculated the cost, you calculated the bias, you calculated the queue length. Now you add the queue length and the bias together, you get this. And the one that has the lowest is this guy here. That means you go out on 3. Because it has the lowest aggregate score. Lowest queue, lowest of the sum of the queue score and the bias score. Right? So this is one example of when you do all this. Of course, the queue lengths are changing all the time, right? Okay? Then the quality of the links may also be changing, especially if it's wireless. Alright, so that's why it's adaptive. Questions?
So the bias is always the multiplication of 3?
No, this is an example.
So it can be randomly.
It will be in 2, 4, 6, 8. 4, 8, 12, 16, up to you. Okay? This is just an example. I just want to introduce the concept of bias. Okay? Huh? Alright. So of course we are always looking for least cost algorithms, and the question is, what is the cost? Okay, so you saw an example of aggregated cost consisting of the link quality as well as the bias value. Okay, right? So good networks, for a given network, the nodes are usually bidirectional. Okay, and the link costs in each direction may or may not be the same. As you saw in the previous example, you see the link cost may or may not be the same. So you see, this one is not the same. This one is not the same. Okay. So the cost of the path will be the sum of all the costs. Sum of all the costs. Okay? And then you choose a path with the least cost. Okay? So for example, in this case, you want to go from A to B. So you see what are all the options that gives you the least cost. And then you pick that one. Okay. Now, this is okay if you've got a small network. This algorithm will not work very well for a large network. Alright? Okay.
Cost is latency.
It can be latency, it can be packet drop rate, bit error rate. There are so many ways to define the cost. Quality of the link, basically. Basically, quality of the link and congestion on the link. And capacity of the link. Because not all links may be the same. Okay, we are now describing this in general for all networks, whether it's wired or wireless. Alright? But those are usually the main performance measures. Quality of the link. Quality means in terms of BER, bit error rate, or packet drop rate. Congestion on the link. So that's where the queue length comes in. And capacity of the link. How many bandwidth of the link? Those are the very common ones. Okay, those three. All right. So this is an example of link cost. So let's say if you go 1, 2, 4, 6, 8. So you got 1 plus 1 plus 4 plus 2. Okay, or you go this way. So you add up the cost. So I think in this case the cheapest one is 1258. Okay, 1258. Because this 1 plus 2 plus 2 is 5. This 1 plus 2 plus 4 plus 2 is 8. 2 plus 4 is 6. I think this is the lowest. Okay. Alright. Okay, so simple networks, fine. Alright? But the network grow is not so easy now. So now I'm going to introduce two algorithms which are very commonly used in routing. By the way, this routing algorithm, Dijkstra, that's the name of that person, Dijkstra algorithm. This is a very common algorithm that is used for your navigator. You know your map navigator? They use this algorithm, okay? Or a modification of this algorithm. It finds the shortest path from a given source to all other nodes. Alright, so let's suppose you have a total of n nodes in a network. The source is little s. Okay, T is a set of nodes that you have considered. I'll show you the example afterwards. W is the weight or cost between node I and node J. Alright, between node I and node J. Of course, WII, which is to itself, cost is 0. Huh? Okay. Alright. And ln is the cost up to the intermediate point or destination. Okay, ln. So let's see how the algorithm goes. Okay, first of all, step one is to initialize. I will go through this step by step afterwards. Okay, initialize the system. All right, to 0, or if they're not reachable, you say that the path is an infinity away. Okay, you initialize it. Then you starting from the source, you look at the weights of its neighbors. Okay, weights of its neighbors from the source to the next neighbor. After that, you find which is the lowest one. Then for that guy, from this source to this guy to its neighbors. So you keep updating the table. Alright? Every time when you consider who needs to consider, you pick the one with the lowest cost. Pick the one with the lowest cost. So this is what this algorithm is doing. And then, previously you may have selected a certain path from node I to node J. But as this progresses, because there's so many choices, right? Some of this path may result in a lowest weight at future iterations, and then you modify it accordingly. Okay, so let's, all right, so this is all described here. So let's look at this. This is an example of a network that I'm going to use. I actually have 2 examples here. All right, and I want to find the cost from node 1 to all the other nodes that is lowest. Okay, from 1 to all the other nodes. So there are altogether 5 nodes here. From 1 to all the other 4 nodes, that is the lowest. I'm trying to find that. Okay, so as I said initially, so what we do is we create a table. This is the table. Okay, this is the table. So if you look at the table, these are the iteration counts. T is the set of nodes that I have already taken into consideration. So right now the set is empty. Okay, because I'm initializing it. L is the cost to get from number 1 to number 2. Node 1 to number 2. And what is the path it takes? Okay, so this is the cost. This is the cost to get from 2 and the path. Cost to get to number 3 and its path. Cost to get to number 4 and its path. Cost to get to number 5 and its path. Okay, so far? Alright, so now you initialize. There is no path to 2 yet because you initialize everything. So I set it to infinity. The cost, so the cost is infinity, the path is not known yet. So this is how you initialize it. So the first step is that, who are the neighbors of 1? The neighbors of 1, where you can go, is node 2 and node 3. Those are the neighbors. Okay, so 1 to 2 will be a weight of 5. Okay, 1 to 2 will be a cost of 5 as well. This is a capital L of 5. 1 to 3 is a cost of 10. Okay, so that's my first step. And 1 has been considered now. And so it goes into the set. So 1 to 2 has a cost of 5, as you can see here, and the path is 1 to 2. The next neighbor is 1 to 3, which has a cost of 10. The rest has not been touched yet. Got it? Next step. 5 is a lower cost than 10. So next thing to consider is number 2. Node 2. Because 5 is smaller than 10. So for node 2, alright, you include it inside here, the set. 1 to 2, you see that it's still no change, so I leave it as that. Then I have 3. 3 is here. It is cheaper to go this way. Rather than go from 1 to 3, it is cheaper to go from 1 to 5 to 3, because 1 to 5 to 3 is 5 plus 3, which is 8, as compared to 10 earlier. So now I have replaced this to go to 3 by 1, 2, 3 with the cost of 8. Alright? Okay? At the same time, 2's neighbor to 14. Alright? 2 to the neighbor to 14. So I can go 1, 5, sorry, not 14, node 5. Alright, so it will be 5 plus 9, which is 14, 5. It is also a neighbor of node 4, so it's 1 to 2 to 4. So 5 plus 2 is 7. You see, I'm updating it every time, you notice? Okay, so now, since the set of this guy is already in 2, so 2 I don't have to worry about because it's already in the set. So then I look, this is 8, this is 7, this is 14. So who the continuous is considered next? This guy, because it's lowest. Alright? Always the lowest first. Okay? So that's the next step. Alright, so this node 4. You see, node 4 is now considered because 7 cost is the lowest at the moment. So if I do that, then again you check. To go to 2 is still the same. To go to 3 is still the same because this is still the lowest cost path. To go to 4, alright, 1 to 4, I can go the same, 7. To go to 5 now, I go 1, 2, 4, 5. 1, 2, 4, 5 is cheaper because it's 5 plus 2 plus 6. 5 plus 2 is 7, 7 plus 6 is 13. So this has reduced. So this is actually a better path to get to 5. Okay? So 1, 2, 4 has been considered already, so I don't have to worry about this number. I don't have to worry about this number. Okay? So which is lowest now? Between 8 and 13. 8 is lower, right? So that means I take node 3 into my set now, the next one. So I take node 3 into my set now. Okay? 1 to 2 remains the same. 1 to 3 remains the same. There's no lower cost path. 1 to 4 remains the same. 1, 2, 4, 7 is it. But 1 to 5, you find that it has changed. It's cheaper to go 1, 2, 3, 5. 5 plus 3 plus 1, which is 9. See, this one has changed. I have updated it. You see it? Huh? Okay, so now the only guy left is number 5 now. Okay, so of course I add 5 to the last one. Again, I check. To 2, still the best. 1 hop away. To 3, 1, 2, 3 is still the best. Give me 8. To 4 is still the best. This is still the best. And to 5, this is still the best. So now, if I keep doing this, no more already, because I've already got my full set here. Okay? So what you see in the Dijkstra algorithm is that it's actually identifying all the routes to all the other nodes, which has the lowest cost. Okay? So if you have 5 nodes in this network, you will have 5 iterations. Because you've got to fill the T set. Yeah, the T set. You have to complete the T set. Okay, if you have 20 nodes in this network, you have 20 iterations. Okay? Any questions? Okay. So I actually have a second example. I will not go through it. I leave you to play around with it. Okay, the results are inside here already. Okay? Second example. Alright? And tutorial has more for you to try. Okay, so my suggestion is you look at this network. Okay, you look at this network and you generate this table. Okay? You generate this table. Okay? Right? Okay, so the other algorithm is called the Bellman-Ford algorithm. Okay? And the Bellman-Ford algorithm is based on number of hops. Okay, it considers all the neighbors that is 1 hop away. Then it considers all the neighbors that are 2 hops away. then you consider all the neighbors that are 3 hops away. That's a Bellman fault. Alright? Okay. So as you consider a wider and wider number of hops, the optimal path will change along the way. Optimal path. Alright? So let's see what happens now. Okay? Right. So this is the description. Again, you initialize the whole thing. Alright? And then you search for the best path, 1 hop away, best path, 2 hops away, best path, 3 hops away, etc. Okay, which is described here. So same network, same link cost. Okay? So let's do it now. Now my table has changed now. I still have my L2 path, L3 path, L4 path, L5 path, etc. But now I'm doing hops now. I'm not doing iterations. So this not iterations is based on choosing and considering the node with the lowest cost, right? Lowest cost to add to the T set. Okay, there's no T set here. It's just going by hops. Okay, again my source is here. So obviously the first one is 1 hop away. There are only 2 guys here. 1 hop away, 1 to 2 has a cost of 5. Then 1 to 2 has a cost of 5. 1 to 3 has a cost of 10. The rest you don't touch. Okay? Right? Okay, next consider 2 hops away. 2 hops away, this is 2 hops away, this is 2 hops away, this is 2 hops away. Alright? So you got all these candidates and you see which is the best. So now this is already brought in because it's 2 hops away. So the lowest cost to get to 8 actually has changed because the 1 hop was 10, 2 hops is 8. So this has changed. Going 1, 2, 3. 2 hops to 4, this is the lowest cost, 7. So it's 1, 2, 4, 1, 2, 4 with the cost of 7. And 2 hops away, the lowest cost is this way because this is 1, 3, 5, which is 11. If I went 1, 2, 5, it will be 14. So I pick 1, 3, 5, which is this guy. 2 hops away. Are you all with me? Now I consider 3 hops away. Okay? In considering 3 hops away, going to 2, this is still the same because this is still the cheapest. Then going to 3, alright? Going to 3, this is still the cheapest. This way. Giving you 8, 1, 2, 3. Going to 4, this is still the best. The 3 hops doesn't help me. This is still the cheapest. Going to 5, 3 hops, 1, come. 5 plus 8 plus 5 plus 3 plus 1, this is 9. Previously, I was also 9 here. 1, 2, 3. So in fact, after that, if you do 4 hops, 5 hops, it's not going to change anymore. So when do you stop? When you don't see any more change. That's when you stop. Alright? You see the last row and this row are the same. That's when you stop for the Bellman fault. Okay? So recap. On Dijkstra, you have to do every iteration. The number of iterations is equal to the number of nodes. For Bellman fault, you do it until the last 2 rows are the same. Then you can stop because there are no more changes. Is that okay? Everyone? Okay. So again, I've given you this example to play. Alright, you should come up with the same result. You can try it. Is that okay? Any questions?
What's the application for this?
Finding your roots. Okay, finding the route from A to B. You want to get from here to Marina Bay Sands. You have all the links and the roads are there. Okay? So if you use an offline map, it doesn't know about the traffic condition. If you use Google Map or Waze, it knows about the traffic condition. So there are new factors coming in. Okay? We have an app that we developed and launched early last year. I hope it works. I don't know whether it works or not. And, okay. So it's ready to find routes. Okay? Whether it's for network routes or pathfinding routes. Okay? Have you used this app before? Anyone use this app before? Okay. So the Pathfinder is using Dijkstrak. Okay? So you can specify, I don't know. I don't know whether it's on it down. No. It doesn't use it down. Okay, let's say I want to go to E1. Okay, doesn't matter which one. Dash 06. Okay, that's what it is. Then you press go. You want to take shuttle bus or you want to walk? Here you should walk, huh? Walk is a good plan. Okay? Right? Starting point. Starting point is here. Huh? E, also LT. LT. 4. Okay. 4. You want to live or stairs? Very easy, huh? So, okay. It's supposed to give me what is LT for? I don't know what I'm supposed to do next. So it's supposed to give me a path, right?
没有带往 lecture theatre for
LT4 is not
Oh, I have to do lecture theatre for. I need that. Walk. Yeah, okay. Where do I go next? It's finding my path. Yeah. So it's using Dijkstrak. There you go. Okay. So basically, with LT4, it will tell me to go, and that's all the steps are here. Pass through this E5 building, walk for 5 meters, blah blah blah, go turn left, turn right, whatever. Okay, and then if I zoom in here, okay, this is where I am. Then pull it down. Okay, yeah. All right, and then you can zoom in. See, it's a zoom in. Okay, this is where I'm starting from, huh? Okay, right. You can see the path, right? That's right. And the levels, okay, it's using Dijkstrak. You cannot drive in the building. Yeah. This is version 1 beta. Okay, I hand it over to another prof to take care of it now.
So it's like every corner is a lock. Every turn.
Yes, all the links have to be digitally put into the geographic information system. So you can imagine all the thousands and thousands of links. You have to put inside, otherwise it won't work. Right? Okay, it all has to be digitized inside. Okay, so that's what pathfinding is. Right? In that case, it's pathfinding. In our case, it's finding a route. You want to send data packet to another location. What's the best route there? Okay? So, just some comments about the two algorithms, government fault, oops, whatever. Okay, so government fault is based on the path calculation and knowledge of cost to all connected neighbors plus advertised costs, right? It is susceptible to loops, all right? So for us, when we do all these simple networks, it looks fairly easy, all right? But it is susceptible to loops, all right? But as I said, you usually stop when the last two rows are the same, okay? Dijkstra again also needs Node to have complete information of the entire topology, and each router requires memory to hold the link state conditions in a database. Okay. Now, obviously, you cannot apply Dijkstra as is, like the way we are doing it. All right, because it will take a long time to search through everything. Okay. All right. Okay. So usually the improved Dijkstra is to partition it into sectors to do it in a much more organized way. Partition it. Okay? Alright. Alright, so those are the routing algorithms that I will cover in this course. Any questions? And the tutorial has example. Lecture note has an example for you to practice. Okay? No question? Okay. Now, you will revisit routing again later with Prof. Tam. Because when he talks about sensor networks later, then there are other conditions that come in that will influence the path that you take. All right? For example, if you are deploying sensors in a forest, you cannot change battery then. Okay? So what happens if certain sensors die? Then your routes will change, right? Okay? Then you might design the routing protocol such that you try to lengthen the life cycle of the network. So you will put less traffic on, say, a relay node that has, you see the battery is going down faster than the others, so that you keep the longevity of the node, of the network longer. So then power conservation comes into the equation. So he's going to talk about all these sort of things later. All right? Even for the MAC protocol that we have done, there will be variations of that. So he will also revisit MAC protocols for sensor networks. Okay? Mainly from the perspective of power energy conservation, but also from the perspective of localization. He's going to talk about localization. Okay? All right. So with that, I'm going to move on and introduce ad hoc network. I won't go into the protocols. I won't have the time maybe today to go into the protocols, but at least I give you the concept of what is mobile ad hoc networks. Okay. Now the networks that we have seen so far are basically infrastructure-based networks. It has a backbone, an IP backbone. All right, they have infrastructure. Okay, and you may have base stations, and then you have mobile nodes, etc., etc. So these are called infrastructure-based wireless networks. Our Wi-Fi is an infrastructure-based network because the backend is connected to the Wi-Fi, to an optical network, for example. Okay. But what if there's no infrastructure, or your infrastructure got destroyed? Okay? What are recent incidents to illustrate that? When the hurricanes hit places like, what's the most recent one? I don't know. There were some hurricanes and typhoons that hit the Philippines, the Caribbean, remember? All this, there's no more infrastructure, gone, all wiped up. Okay? I'm very active in IEEE, and I have friends in Philippines, and there was a very bad typhoon about 3 years back. The whole province was affected, everything was wiped out. So what they did was, in many places we have IEEE branches. So they gather a group of people to bring in supplies in, to put in solar panels, and to put in this infrastructure called mobile ad hoc network so that people can communicate. Not the users and victims, but the civil defense people, so that we can coordinate the rescue missions. Because they are more important, they need to communicate with the other emergency response teams, right? If they cannot communicate, then how can they coordinate all the supplies coming in? All right, okay? Of course, it's important for the victims to contact their family members, right? But during the first 48 hours, who is going to be more important? The emergency response, right? Than the victims itself, because they're there to help the victims. Okay, so when you don't have the infrastructure, you need an alternative communications infrastructure, or communications network, if you like, and that's where ad hoc networks comes in. So these are examples where ad hoc networks can come in. Factory automation, disaster, I already mentioned disaster, and even car-to-car communication. Okay, so 802.11p is a hybrid of an ad hoc network because it still communicates with an infrastructure. It's still a hybrid. Okay, so that motivated the design of ad hoc networks. Okay, so ad hoc network is a collection of wireless mobile hosts or nodes forming a temporary network without the aid of any established infrastructure or centralized administration. The main differences are the following. It's wireless, it's self-starting, that means it configures by itself. It doesn't need an administrator. Alright? It cannot assume that every node is within communication range of every other node. That means it is a multi-hop network. Okay? And its topology is dynamic because the nodes are moving around. Okay? So, what are the challenges? Given that you don't have a fixed infrastructure, then you must find a way from one node to get its data to another node through the multi-hop network. And that's where different routing protocols comes in. Okay? The nodes operate on battery power, so sometimes you may have to think about conserving that power. Alright? And again, the topology, that means the configuration, is dynamic. And what are the considerations? Of course, if you like a system that is simple, reliable, efficient, it should be distributed because there's no central control. Okay? Lightweight, quick to adapt to changes, either in topology or the traffic pattern. Protocol reaction should result in minimal control overhead. It should be bandwidth efficient. Then because things are moving around, you should be able to handle handoff. Okay? Handoff meaning that if I'm talking to you and it has to go 1, 2, 3, 4 and he moves away, or you move to some other position, somebody else has to relay a different path. There's any more? Okay? So in many situations, then the peers may not be in communication range with one another. Hence, you basically need a multi-hop network. Okay, so mobile ad hoc networks are typically multi-hop networks, and there are 3 categories of general categories of networks. The first one is on-demand routing. That means when I want it, I find a route on demand, source initiated. Okay, A wants to send to B, then he initiates a discovery for a route on demand. Okay, so it is what we call reactive routing. because it is reacting to a need, okay? And it only creates nodes as and when desired. The second is table driven. So this is a proactive. So I keep updating my tables. If changes occur, I update. That's called proactive. Okay? Maintain consistent up-to-date routing information from each node to every other node. Okay? Then the third was a hybrid of these two. Hybrid of these two. Now, in this module, I will not be able to give you too many examples because it takes too much time. All right, I will only go through the three in red. Okay, so ad hoc routing, you have the table driven, which is proactive routing, and the source initiate on demand, which is reactive. This is only a small snapshot of the hundreds and hundreds of different protocols all the different researchers have come up with. All right? This has been an area that has been actively investigated for the last 2 decades. Okay? So for the table driven, I will be looking at destination sequence distance vector. For the source initiated, I will be looking at ad hoc on demand distance vector, AODV, and the dynamic source routing, DSR. Okay? All right? You want to read more? I got the reference list for you. Okay? You can find out more. All right? Some of you who are interested in this area for research, after you listen to Prof. Tam, maybe some of this might excite you, and you want to do a PhD in this area. Oh, great! At least we influence you. Okay, but it's a well-researched area and it's getting narrower and narrower in terms of opportunities for new inventions, because we've done for quite a number of years. If you asked this question 15 years ago, there are so many things you can do, but time has moved on. Okay, so in fact, it's very hard to find money to do this sort of research now, because it's maturing. So many of us, we are not doing the protocol part. Many of us are moving to the cybersecurity part. How to make sure these are safe. That's where the money is. Okay? Right. So of course there are trade-offs. Okay, the first is latency. So obviously, if you have to discover your route on demand, it will take longer, correct? Whereas if you have been keeping all the routing tables, there it is, immediately you can use it. Okay, so latency, proactive ones will definitely have lower latency because you don't have to discover the route. All right, reactive ones will have longer latency. The second is overhead. Now, if I have to keep my tables up to date, there's a lot of overhead, you know. The amount of traffic exchange, message exchange between all the nodes, just to maintain the table will be humongous. All right? So, what that means is that table-driven protocols are not very scalable. For small networks, okay. For big networks, you know, very hard to keep it up to date. Keep the tables up to date. Okay, for big networks. Okay? What is big? What is small? Rule of thumb. Okay? Network not more than several hundred nodes. Okay, manageable. When it goes thousands and tens and thousands, not so manageable. That's big. Okay. Right. So as I mentioned, the two red ones is what we'll cover for on-demand routing. Okay, AODV is a very well-known protocol. Okay, so it's part of the IETF standard. Okay, not IEEE, IETF standard, RFC 3581. Okay, and dynamic source routing is the other one, so we will cover this too. Okay, so on demand means that you discover the routes as and when you need it. Okay, as and when you need it. The source has to discover a route to the destination. However, if some intermediate nodes happen to know how to get a destination, then you don't have to discover all the way to the destination. You just discover from the source to the intermediate node who has knowledge about how to get to the destination. Okay, so that can be used as well. Then that will shorten your search time. It also should include methods to repair the route in case there are problems, especially if you're dealing with an ad hoc network where certain links may have broken. So there must be a mechanism for route repair. Okay, that's the last protocol. Routes have to be repaired in case topology changes or some other problems. Okay, most of them have that capability. All right, so let's start with AODB. All right, so AODB has both the route discovery part and the route maintenance part. Maintenance is required when something breaks. All right, or when changes in the topology occurs. It tries to minimize the number of broadcast messages. It uses symmetric links, and the two main messages that are used in the discovery of the route is the RREP, route reply, and route request. Okay, I will show you what happens afterwards. It also maintains, every node also maintains a routing table, a small little routing table. Okay, that routing table is updated when the particular node sends something out and receives something, okay, or it is dropped from its neighbors. Okay, so it has neighborhood information. Okay, based on that routing table, in the route discovery procedure, then the reply for the route request, the RREP, can find its way back to the source. So all the mini routing tables in the nodes, they will be able to find its way back. Okay, that's how it works. All right, so it also uses this thing called hello messages. Hello messages is to announce your presence and your attributes to your neighbors. Okay, hello messages. A special form of RREP packet. And as I said, they have a routing table which is updated based on listening to the neighbor's transmission, eavesdropping. Okay, right? Unlike DSR, I will tell you what DSR does, which is slightly different. Okay, DSR doesn't have routing tables. All right. So as a result, the packets do not carry information of the whole route, but rely on the tables to get back. Okay. It's a variation of this DSDV protocol, but I'm not going to talk about DSDV unless you want to read. I got a paper inside of this. Okay. Then he has this thing called monotonically increasing route sequence numbers are used to supersede stale cache routes. So there is this thing called the sequence numbers that give you an indication of how old a route is. So if it's a sequence number that's very old, you know that this is not a very reliable information anymore, and you may not want to use it. Okay, so in the routing table, these are the fields. You can see the sequence number there. You can see the IP address of the destinations, all right, and some other things like hop count and so on. Okay, right, and it looks something like that. All right, for the RREQ packet. Okay, so these are the details. Okay, let's see what happens. A wants to find a path to F. Okay, A wants to find a path to F. So what does it do? It sends out and broadcasts an route request packet, RREQ. His neighbors B and C hear it. B said, I don't know where is F. C said, I also don't know where is F. So I broadcast out the RREQ to my neighbors. Okay, so it broadcasts out to D. D said, maybe D might know, maybe D might not know. If not, he will send the RREQ to E and F. If he doesn't know, he will send the REQ to F. F said, hey, I'm the destination. So now I send back a REQ, a REF, root reply. Problem. So root reply, so it goes backwards. Find the root back. Because of all the routing tables there. And the sequence numbers that are available. Okay? Alright? Details of all this you can find in the paper. So I won't have time to go through. So these are examples of the routing tables that are created over time. Okay? Alright? You can also search this guy. This is where I got his thing. That's why I put a courtesy. I didn't actually ask him, but I must acknowledge I didn't get that the content came from him. Okay. Alright? So it's actually a very simple mechanism. Now, what happens if things go wrong? That's where the root maintenance takes place. So let's say now F has moved. Okay, F has moved. Just now it was here, right? See, just now it was here, right? Suppose now it's moved down here. So this link has broken. This thing is broken. Okay? How do you know it's broken? Remember, everybody is sending out hello packets, right? Then suddenly, D says, hey, I haven't heard hello packets from F for a long time. Huh? Something must have happened. So whatever path I have to F previously is probably not valid anymore. Because I didn't hear a hello packet from him. Right? Okay? So what will happen is that when this occurs, then there will be a request to do a